In this section 5.2, we're looking at using perpendicular bisectors. If we start off, we need to first be familiar with some terms. A perpendicular bisector is going to be a line that's perpendicular to a segment at its midpoint. So we look here, we have line CP. It's perpendicular to AB at its midpoint P. So in this case, CP is the perpendicular bisector.
Sierra Bowerson, please come to the front office at this time. Sierra Bowerson, please come to the front office.
We also have the term equidistant, and we're just going to think of equidistant as meaning the same distance. So if I have P as a midpoint, I know that A and B are equidistant to point P. So we take those terms, and now we're going to get to our first theorem, the perpendicular bisector theorem. And that says, in a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So, again, our perpendicular bisector is CP. The point we're looking at is C. So let's start off by saying if CP is the perpendicular bisector, and of course that means we're looking at point C. Point C is equidistant from the endpoints. Well, the endpoints are A and B. So we were going to say CA equals CB. Before we mark that on here, let's first realize that this is a perpendicular line. These are actually two right angles at that perpendicular. I have congruent angles from a midpoint. I have CP works with reflexive property. It's congruent to itself. So really I have two triangles here, APC and BPC, which are congruent to each other by side, angle, side. Now, because those are congruent, we get that all the parts are congruent, and that's by the fact that corresponding parts of congruent triangles are congruent, or CP-CTC. But that really leads to the fact that CA equals CB. Furthermore, if we look at this line CP here, it's almost like a mirror image of these two congruent triangles. So if I knew this value, CA, it would be the same for CB. PA would be the same as PB. So, look at our example here. Given that M is the perpendicular bisector of LD, we know that TD is 3 times x plus 8, and LT is 5x. We need to find LT. To find LT, we have to find x, so let's go with 5x equals 3 times x plus 8. And again, these are equal because this is a perpendicular bisector. When I'm solving here, I'm not going to divide both sides by 3 because that would give me a fraction that I can't simplify. So let's just distribute. I get 3x plus 24. If I subtract 3x from both sides, I get 2x equals 24, or x equals 12. I need to finish up by finding the value of LT. And LT, let's see, let's plug it into 5x. We get that LT is 60. LT would be 60 as well as TD as well, because if we plug that in, it should be the same. In fact, 12 plus 8 is 20, times 3 is 60, and it is the same. Next, we look at the converse of the perpendicular bisector, and this is just going to take the different approach, still looking at the same ideal properties. And says, in a plane, if a point is equidistant from the endpoints of the segment, so I'm going to start with D being the same distance to A and B. Then it is on the perpendicular bisector of the segment. So what we're saying here is if this point is the same distance to A and B, it's actually on our bisector CP. And that, of course, is stated as, then D is on the perpendicular bisector of AB, which of course is CP. And really, if I'm looking at AB, anytime I have a point that's the same distance from it, it's going to be equidistant. Like point P. Point P is the same distance from A and B because that's a midpoint. D, even C, really any point I put on there will be the same distance. Okay, look at an example. Now we have LT is 27.4, UD is 23.8, DT is 27.4, and they want us to find LD. Now if we look at this one, we have this point T is equidistant to L and D, like we had here, equidistant. So since these are the same, it's on the perpendicular bisector, which is M, which now tells us these need to be the same, which means this is 23.8, which eventually gets us to LD being 23.8 plus 23.8, or 23.8 times 2, which is 47.6. If we look again, these are mirror images here. We have the 27.4s, they match up. The 23.8s are going to match up as well. If you notice, it's just a lot of setting things equal and simplifying. Next, we're going to our concurrency of perpendicular bisectors of a triangle. So now instead of just having one side where we have a perpendicular bisector, we're now taking a triangle and taking the perpendicular bisectors of all the sides. And if we do that, we actually get those lines, those perpendicular bisectors meet at a point. So we say the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. So let's start off here. Our perpendicular bisectors are PD, PE, and PF. Now if I have that, they meet at point P, and they're equidistant from the vertices. Well, equidistant to the vertices means P to A, P to B, and P to C are all the same. So this point is the same distance to A, B, and C. For example, if this was 10 units, this would be 10, this would be 10. Now let's get a little more specific. We have the term concurrent lines, or three or more lines that intersect at a point of concurrency. And we have that here. These three lines we started with, PD, PE, and PF, all meet at a point. We call that a point of concurrency. But we're going to be more specific here, and we're going to call it, when it's perpendicular bisectors, we're going to call this point the circumcenter. So that's going to be circumcenter P. And that again is where the perpendicular bisectors meet. And it is equidistant to the vertices. Now, in this triangle, which happens to be acute, we notice that's the location of the circumcenter. If we take different types of triangles, if we take an acute triangle, like we had, that circumcenter P will always be inside the triangle. But if we start to change it and look at maybe a right triangle, that circumcenter actually is on the triangle and it's on the hypotenuse. And if we went forward and looked at an obtuse triangle, the circumcenter in this case would be outside the triangle. And that's fine. It's just the point where they all happen to meet. Acute, right, and obtuse will all meet at a point. It's just the type of angles determines where the location is. So if we look at this last example, we have a triangle ABC. And if you read the question, they're trying to find a location in the middle that's the equal distance to each endpoint, or A, B, and C. So to find this, we want a point that's equidistant to the vertices or equidistant to the letters. And to do that, well, it's what we've been talking about, our perpendicular bisectors. Now we're just going to sketch it out and get an approximate here, but I take a perpendicular from the midpoint, perpendicular from a midpoint, and perpendicular from a midpoint. And we get they meet at this point, which again we call the circumcenter. And this will be equidistant to A, B, and C. Now, this is not an exact, this is just a basic sketch, but that's maybe something we had. If we had a triangle and we want to know some point that was equidistant to the vertices, or our 3 points, and try to find some point that's equidistant